Hi everyone, we're back again now to talk through Chapter 18. We're going to focus specifically on probability models and on some more complex models than what we talked about in Chapter 17. I will be very honest with you, this is going to be challenging material. So you might need to watch this particular lecture presentation more than a couple of times, or more than one time at least. We're going to be talking about a concept called sampling distributions, and just from past experience I know that can be confusing. It's a rather theoretical concept, but I hope when going through the slides and some examples that I can try to make it more concrete for you. And we'll definitely do a lot of practice so you can see this over and over again, and hopefully you'll soon realize why it's so important. So I'm beginning here just on the cover slide here with another cartoon, which is all about randomness. I thought this related well to what we've just talked about in Chapter 17, and a nice quote down below from a scholar all about, again, this idea of randomness. So I encourage you to look through these things and again, think about how they relate to what you've been learning about. So just as a quick review, I have some questions here I want to ask you. So here are a couple of statements. There's something wrong with each statement, and I want to see if you can figure out what's wrong. So I'll show the statement, think a little bit about it, and then I'll reveal the answer. So first, the probability a randomly selected driver will be wearing a seatbelt is 0.75, whereas the probability the driver will not be wearing a seatbelt is 0.3. So hopefully you're thinking about the fact that if you're in a car driving, you have just two options. You can wear a seatbelt or not wear a seatbelt. And so if we think about both of those probabilities together, we would expect the sum to be 1. And obviously here, if you add 0.75 to 0.3, you get something greater than 1. So that would not be a legitimate probability model. How about this one? The probability that a randomly selected car is red is 1.2. So hopefully you're thinking about the fact that a probability cannot be less than 0 and it cannot be greater than 1. So we would not have something as large as 1.0. So remembering that certain numbers can only have, or certain concepts and ideas can only take on certain values, that'll definitely be very important moving forward. Probabilities in particular can only be between 0 and 1. Okay, so let's review some other things here. So let's say I tell you that we have a bag of Reese's Pieces, and the bag contains 50 candies. And we have, there are 3 different possible color options. Let's say we have 20 orange, 12 brown, and 18 yellow in our 50 candies in our sample. So here we have a sample of size 50. So if we were to write this as a probability model, think about what that would look like. So remember, with a probability model, you list all your outcomes. In this case, it would be our 3 different colors, and then we list the probabilities associated with each of those outcomes. And here are the candies, just so you can better visualize this. Now, what's the probability that you will reach into the bag and obtain a yellow candy or a brown candy? So hopefully this is pretty easy for everyone. It relates back to what we talked about in Chapter 17. Yellow or brown, we would just add together those 2 different probabilities here. So 0.24 plus 0.36, that'll be 0.60. Or we could think about it a different way. We could say, well, if it's yellow or a brown, then it's obviously not an orange. So we could just take 1 minus not orange to get our example, or to get our answer. So again, that kind of leads into the next question. What's the probability that you will not choose a brown candy if you randomly reach into the bag? So again, the probability of something not occurring is 1 minus the probability that it does occur. So that would be 1 minus 0.24 or 0.76. Okay, so again, I wanted to go through these examples just to review what we talked about in Chapter 17, just to get that fresh in your minds, because this does relate a lot to what we're going to now talk about. And And that's this idea of a more complex probability model. So again, what do you think type question. If I toss a fair coin, the probability of the coin landing on heads is 0.5. So I'm hoping everyone agrees with that. We talked about this back in chapter 17, why that's the case. We know in the long run, if we toss it over and over, we'll see half the time it's heads, half the time it's tails. Here's a little bit of a more complex question. What do you think about this one? If I toss a fair coin 100 times, what is the probability it will land on heads 65 or more tosses? So 65% of the time or more. Or what's the probability it will land 65% of the time or more on heads? Okay, so this question's a little bit more complex. We're not dealing with one particular outcome, one toss of the coin. We're thinking of a sample of 100 tosses. What would that sample outcome be? If we could toss it 100 times and look at the proportion of heads, what would we see? So to answer a question like this, we really have to focus on what we call probability models for samples. And chapter 18 delves into that. In the early part of the chapter, it starts talking about this. And this is where things get a little bit complex, because to understand the probability of getting a particular sample outcome rather than an individual outcome, you have to now think of something called a sampling distribution. And we're going to talk through the characteristics of that distribution first here in chapter 18, and then we're going to revisit that in the first part of chapter 21, which will be the next set of lecture materials. So let's go back to this rhesus pieces example and think about what happens when we focus on samples. So in the previous example, just a couple slides before this, I mentioned that we had a sample of 50 candies and we were looking at the proportion of brown, yellow, and orange within that one sample. So let's imagine that I want to know, I asked some questions then. So we followed this up with some questions, and I asked you, what's the probability that you reach into this bag of 50 candies and you pull out one brown or one yellow or a yellow or an orange? Okay, so we were focused just on one single candy. Now what we're going to do is we're going to focus on a sample. So we want to know the probability of obtaining a certain percentage of orange candies from a sample of size 50. So again, I just want you to notice that suddenly we're focusing on the outcome of a sample, not of just one individual case within a sample. That's going to be a really important distinction. What is the sample outcome going to be? So if a bag of 50 candies is a sample, the proportion of orange candies in that bag would be a sample statistic. So we're going to go back now. Early in the semester, you learned the difference between statistics and parameters. That's going to be really important now moving forward. So samples give us statistics, populations give us parameters. And in this case, the sample statistics is sample proportion. And you're going to see some notation now. You're going to see a P that stands for proportion, and it's going to have like a little, it looks like an upside down V. We call it a hat. So sometimes we call this P hat. In words, we'll call it P hat. That's our sample proportion. Now, although we might only have one single sample to work with, so we take one sample, we want to answer some questions about this. To really be able to understand those questions, or to really be able to answer those questions, we have to understand how our sample statistic can vary from sample to sample. So if we want to answer a question about one single sample, we have to have this understanding of how our sample and how our statistic could have been different if we had taken a different sample. So we have to have this understanding of this idea of sampling variability. If I take a sample, I'm going to get one particular outcome. If you take a sample of 50 candies from the population, you might have a different proportion that are orange. If your classmate takes a sample of 50, he might have a different proportion that are orange. So from sample to sample, if we're each randomly selecting, we're going to see some variability from sample to sample. But over time, if we kind of think about all the possible samples we could obtain and look at all those statistics, we're going to see this regular pattern emerge. So that's where this idea of randomness comes back into play. Over time, if we look at all these different sample statistics, we're going to see a regular pattern start to emerge. And in a moment, I'll show you what that pattern looks like. First, though, I just want you to understand this idea of a sampling distribution. So this is a big new term. It's going to follow us for a while now. A lot of what we're going to do now moving forward is going to rely on this underlying idea of a sampling distribution. And we want you to understand the basic ideas of what a sampling distribution is. So first of all, we just want you to imagine that you have chosen a random sample from a population. You've calculated a statistic from your sample. Here we're going to focus on the sample proportion, but soon you'll learn there are other statistics we could calculate, like sample means. So we talked about that back in chapter 12. So again, you've taken a sample from a population and you're looking at a characteristic of that sample. You've computed a sample statistic. Imagine now that you repeat this process many times. So rather than just taking one sample, let's say you go back to the population and you take another sample, and then you go back and take another sample. You keep doing this. You keep taking random samples. Each time you're going to get a different statistic. And let's say that you decide you're going to, you find out what the statistic is, and then you're going to graph that statistic. You're going to put a histogram together, for example, of all your different statistics. So you have lots and lots of samples you've taken. Each time you get a statistic, you compile all those statistics together into a distribution. We call that a sampling distribution. And that's a certain kind of probability model because it's telling us all the possible outcomes and the probability of each of those different outcomes. So all the possible outcomes would be all the different sample statistics. And we could figure out the probability that you would get particular sample statistics. So a sampling distribution shows us how sample statistics can vary, and it assigns probabilities to the values that the sample statistic can take. So this is really important. A sampling distribution is a collection of sample statistics. That's really important to keep in mind. All the points that you see on the distribution are each come from a sample. Each is a sample statistic. So I'm gonna pause here. We're gonna come back and we're gonna see this in action so you can actually visualize what it is I'm talking about, and then we'll look at some actual problems where you would need to apply an understanding of the sampling distribution, where knowing the characteristics of the sampling distribution will help you.